Okay, so the actual unit is not just trigonometry, it's trigonometry, exponential functions, and logarithmic functions. So there's three meaty kind of analysis of functions here. We're going to start off with trig to start with, which I think, you know, if you did maths extended last year, you don't have to have it if you did. Typically it proves to be a little bit more of a challenging unit, but we start off fairly straightforward and we go from there. So in today's lesson we're going to review right angle trigonometry, and for the rest of the week we're going to be looking at a brand new version of measuring turn. Secondly, we're going to have a look at two brand new rules called the sine rule and the cosine rule. Again, if you've done maths extended last year, you've probably covered these already. Although I kind of feel like as if maybe you did trig at the end or something like that, so you haven't covered it that well. Is that about right? Yeah. So let's just go back to the very, very beginnings, but I'll be really quick with it, just to remind you, because this is really from grade 9, I think, right angle trig. So just a reminder that we have a right angle triangle with a right angle here, and we arbitrarily select one of the other angles and call it theta. So very, very common to use the Greek letter theta to describe another angle. Other Greek letters are often used for angles as well, but theta is usually the first one you pick for an angle, just like x is often the first one you choose for a length. Now, what we do then is based upon where theta is, we define the sides of the right angle triangle as follows. The one that's opposite the angle, we just denote that as opposite. The one that's the longest side of the right angle triangle, the longest side or the side opposite the right angle is the hypotenuse, just to remind you, not the hippopotamus, but the hypotenuse. And that leaves the one that's left over, which we call the adjacent side. Now, adjacent is just an English word which means next to. And there are two sides that are next to theta, but this one's already been claimed. So we're left with calling this one adjacent. Okay, so opposite, adjacent, and hypotenuse are the three sides. And what some clever people in the past, some clever ancient Greeks worked out in the past, might have even been earlier than that, I'm not too sure, is that when you draw a right angle triangle like this, so that there's an angle theta here, then whether the triangle is this size or whether the triangle is this size, when we compare two of the side lengths and divide one by the other, we always get the same value. In other words, I haven't drawn it very big, sorry, but here we go. If I divide the opposite side by the hypotenuse, I'll get a value in this little triangle. And if I divide this opposite by the hypotenuse, I'll get exactly the same value. In other words, these are called similar triangles. They look the same shape, because all three angles are the same. So the only thing different is their side lengths, but the ratio between any two given sides ends up being exactly the same value, which is great. Because if that's constant, then we can make a table of values. And if this was, say, 20 degrees, then this opposite divided by this hypotenuse will be the same as this opposite divided by this hypotenuse if the angle here is 20 degrees. So we can have a table of values, and if we've got a table of values, we can look them up, which is really handy for solving missing lengths problems and stuff like that, which we'll have a look at in a second. Of course, after calculators were invented, we were then able to store that table of values inside a calculator, and so when I go sine or cosine or tan of 20 degrees, it can give me spit out a value for me. So that's just the short history lesson there. Who can remember what, I just said them, probably not much of a recall here. Who can remind me of what those three trigonometric ratios are? Just the names of them, not how they're defined. One of them? Sine, thank you. Next one? Say it loud and say it proud. Tan. And last one? Cos. Okay? To give them their full and glorious names, the longer name for sine is sine, the longer name for cos is cosine, and the longer name for tan is tangent. Okay? So sine, cosine, and tangent. Now here's the trick one. Each of those three words represents a different pair of sides that are being divided by. Okay, different ratios. Okay, so who can remember what two sides do we divide for sine?
Opposite over hypotenuse.
Very good. Who can remember what two sides we divide for tangent?
Adjacent.
Opposite over adjacent. And what two sides do we do for cosine? They're the two sides, not quite the right order. Yeah, adjacent and hypotenuse. Good. Okay. So we've got sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And that pretty much covers every single combination, right? There are also three other functions which go the other way. So adjacent over hypotenuse, hypotenuse over adjacent, hypotenuse over opposite, and adjacent over opposite. There are three other functions. Did you cover those in 415, Sam?
Yeah.
What were they?
I think it was about cotangent.
Yep. Cotangent.
I forgot ones.
Secant.
Oh yeah, secant.
Sec. And it's all right. Cosec. Yeah. So they're basically the flip of the fractions here. Now I'm confident that most of you would have remembered, would have some sort of mnemonic for remembering those three ratios. Does that look familiar? Sakatawa? Anyone learn anything different? The other one is Old Harry. If you remember it's sine cos tan, Old Harry and his old aunt is another one. Okay, it just sort of depends. So we've got sine is opposite over hypotenuse. So sine is equal to opposite over hypotenuse. Sorry for the different colour I meant for today. Cosine is adjacent over hypotenuse. So cos equals adjacent over hypotenuse. And tan, or tangent, is opposite over adjacent. So tan is opposite over adjacent, like so. Okay, any questions on that? This is just a quick review because I think everyone should have come across this before. Just a reminder. So Sokotawa, remember it. Make sure it's that kind of word that you can use so that when you get into an exam or test, just write it down, Sokotawa, and then come back to Elaine and remember what they stand for. Sokotawa, Sokotawa, Sokotawa. Okay, it turns out that these are just ratios, right? They're just ratios. So pick one side, divide by the other side, whatever that number is either the sine, cosine, or tan of that angle. Okay? It turns out that when we start exploring these ratios, sine, cosine, and tan, it turns out that these ratios behave like functions. So that I can input, remember a function is something that you have an input, processes, and then it outputs something. It turns out that sine, cosine, and tan operate like functions. There are a special group of functions called periodic functions, which means they repeat after a certain amount of time, and we'll look at that in the second part of this trig unit. But this is just a where we're headed with it, looking at these trigonometric or circular functions. Okay, so this again is just a recall. So there are basically three steps to working out one of these sorts of right angle trig problems. Number one is work out the ratio. This is how I would do it anyway. Sub in what you know, then solve it. That's basically it. Let's have a look at two problems and two related concepts here. I'll leave that zoomed out now so that you can sort of see it. So concept number one is elevation, angle of elevation. So when you hear the word angle of elevation, it's talking about the angle that is made with the horizon and angling up towards some object. Okay, so in this classic example here, I have Horatio on his boat. There's Horatio. And he's a certain distance away from the cliff. he knows that the cliff is 200 metres from sea level, and Gerald is waiting on top of the cliff. Now, Horatio has enough petrol to travel another 200 metres. Can Horatio crash into the cliff? I like to make these problems as high stakes as I can. Will Horatio crash? Sorry?
Petrol on the side of both.
Yeah, two-stroke. What can I say? Oh, yeah, good point. Is that better? The sail is broken and he's forced to use his outboard motor, and therefore he's only got... Okay, does that work now? Gee whiz, critical crowd. All right, so what we do is we work out what we don't know. What I tend to do is I tend to pull out the triangle like so. Oh, that's a bit too small. So I pull out the triangle and I put in the information that I know. What? I put in a variable for the thing I don't know, and the angle of elevation, like I said, is always taken from the horizon or parallel to the horizon. So I'll put my dotted line here, and we can see there's a 35-degree angle. Now, people can use measurement devices called a clinometer, by the way. A clinometer is a measuring device that measures turn from the horizon. So if they're looking at it like this, it'll say 0, and if they look up towards the top of the cliff, it'll then read, in this case, 35 degrees. Does that make sense? So that's the measuring instrument, a clinometer. So I know that it's 35 degrees, so I'll put that into my little triangle there, and now I'm ready to go. I know what I need to know. So what I'm basically doing is I'm looking at where the angle is that I have, and I'm asking myself, what are the two sides that I either have or need to know? From the relation of this angle here, I have 200, which is opposite. From the relation of this angle here, I have x, which is adjacent. So looking at Sokotoa, it's got to be tan, right? So my next step would be then to write down tan of 35 degrees, that's what I've been given, is equal to opposite over adjacent, straight plug in. Now, where you go from here is up to you. Some people like to evaluate tan of 35 first. I don't. I like to do a rearrangement first. So the x is on the bottom, and I need the x to be on the top. So I'll do it in 2 steps, but you can really do it in 1. So I would multiply both sides by x to get tan 35 is equal to 200. And then I'll divide both sides by tan 35 to get 200 over tan of 35. Okay, and now I'm going to work that out on my calculator. Now this is where, if you've got your scientific calculator and your GDC, you would be reaching for your scientific calculator, because the thing that I'm going to try and get you to do is work out that if the angle is in degrees, you're going to reach for your scientific calculator, but if it's in radians, you're going to which we'll look at tomorrow if you don't know what they are. If it's in radians, you're going to reach for your graphics display calculator. Having said that, I'm going to use my GDC just so you can sort of see it in action. Just so I basically want you to see where the trig functions are. So I'm going to create a new document, and I'm going to add a calculator. And you can see I need 200 divided by tan of, you can't see it, but I need 200 divided by tan of 35. So I've got 200 divided by, and then it's just over here. Can I make that bigger? Yeah, that's better. 200 divided by, there's a little button that says trig, and there's all the trig functions there. These top ones are your basic trig functions. You only have to worry about the first 3. And these bottom ones are the inverse functions, which I'll talk about in a second. Now, I've already chosen tan, so I click on tan, and then I type in 35. Press return, and it's 285.63 metres away. Will Horatio make it to the cliff? No, probably not. Not unless the drift is good enough to get the Horatio to the cliff, because the engine will cut out after 150 metres. Okay, so I'll go back to the screen and talk to you about that in a second. Just a quick bit of GDC work then. The reason why this worked is because if you've got one of the blue calculators, Marissa, can you just hold that up? See how it's got a blue back to it? If you've got one of those calculators, if you use your little cursor pad, which is really annoying, but if you use it to go up here, you can quickly switch between degrees and radians here. You need to make sure it says degrees if you're going to use your GDC. Now, by default, I've made you set all your calculators up to be in radians. If you've got an older style calculator, you have to change it in the settings, and I'll show you how to do that later. I'll show you what it looks like without it. That's what you'd get without it. That's the radian measure, as you can see, is massively different. So you need to make sure it's in degrees. Okay. Sorry. I'm sure I'm confident that I know all this. I'm not sure if you know it or not. But certainly when you're listening back at the video, you don't want to hear me waiting for people to stop talking. Yeah. Look, I don't mind. If you want to just use your GDC, that's all good as well. If you're happy to switch between degrees and radians and never make a mistake, that's all good. I'm just telling you what will help you not make mistakes. So there you go. So it's 285.63. I'm just writing this down on my iPad and then I'll switch back. There we go. So it's 285.63. And it's meters. So I didn't give a context for this problem, but that's the end of the problem as it says on the thing. But if I did say, will Horatio get to the cliff? The answer is not likely unless Horatio fixes Horatio's sail, and then they'll be right. Depression. I'm not talking about a mental illness here or a state of being. I'm talking about angles of depression. And angles of depression are always taken from parallel to the horizon as well, but in this instance, looking down. So, Horatio has got to land. Cuddles, his cat, is stuck up a tree. If this is an angle of depression problem, who's doing the looking, the cat or the human? It's got to be the cat, doesn't it? Because it's an angle of depression. So, Cuddles says to Horatio, help, help, I need to get down and I'm stuck up a tree. Poor old cat. And Horatio says, I'd love to help you down, but I can only climb a maximum of 15 metres before I get too tired and fall out of the tree myself. I don't know whether I can save you or not. Do you know how high up the tree you are, Cuddles? And Cuddles says, I don't know how high up the tree. I just climbed and climbed and climbed. But luckily, I brought my clinometer with me. And so Cuddles was able to take a measurement of the angle between Cuddles and Horatio. So when Cuddles did that, Cuddles noted that the angle of depression was 50 degrees, and that's what it means. Parallel to the horizon, looking down. Now, there's one other thing I should say as well, and that is Horatio is also, with tears streaming out of his eyes, is looking up at Cuddles. He doesn't need a clinometer, but his angle of elevation is 50 as well.
The Z rule.
The Z rule, yep. So way back in grade 8 maths, if you came from Friends, we learnt that if two lines are parallel and cut with a transversal like so, this angle is the same as this angle. Or if I go the other way, this angle is the same as this angle, and it makes a backward Z or a forward Z in there. So those angles are identical. So the angle of elevation, if Cuddles and Horatio are looking at each other, the angle of elevation is identical to the angle of depression and vice versa. So when Horatio needs to work out how tall the tree is to see whether he can save Cuddles or not, I hope this ends well. I really can't remember whether I picked a high number or a low number. I'm feeling anxious for Cuddles now. I shouldn't have named the cat. It's always the worst thing. What we can say is we can look at the length of the height of the tree. That's what we need to try and figure out. What we could do is we could go up to here and say this is X, and that's fine. Or, I'll undo this in a second, or you can take an angle down here and call this X because that's next to the height of the tree now. and then you'd be good to go, right? Either way is fine because of that Z rule. Okay, angle of elevation equals angle of depression. I'll go from the upside down triangle, but it's up to you. So we go about it. We say we've got an angle here of 50 degrees. Our unknown is X, that's opposite. And the other length we have here is how far away Horatio is from the tree, which is 12 metres. So that's 12 metres up here as well. So we've got opposite and we've got adjacent. So guess which one that is? Don't guess, know it. Tan. Yes, it is tan. Well done, Puddles. So tan of 50 degrees is opposite, this time opposite is on top, over adjacent, which is 12. So you do a straight substitution, which means that X is equal to 12 multiplied by tan of 50. And that is equal to, and I'll go back to my calculator and solve that one. 12 multiplied by tan of 50. You can just type it in for the tan, sine and cos like that. And that gives me 14.3 metres. How far could Horatio climb? 15 metres up a tree. So is the cat saved? No. The cat isn't saved. Why isn't the cat saved? Almost got there. Could grab a paw before they both came tumbling down. What do I need to include? Say it loud, say it proud. What do I need to include? Will? It's from eye level, yeah. So if we say that Horatio is 2 metres, give or take his forehead, then we're going to have to add 2 metres onto that to make... I don't normally have to say the phrase give or take a forehead, but I have this time. So the tree height is 14.3 plus 2, which equals 16.3 metres. And unfortunately, Puddles is stuck up a tree until Horatio can go get a ladder. You haven't been able to see any of that, sorry. There we go. There's my calculations there. I'll just zoom up just so you can see it. Okay, so what I wanted to do here, I've got one more example to show you, a very straightforward one. No cats were harmed in the making of this video. I've shown you an elevation problem, I've shown you a depression problem, and shown you how you can use, figure out which ratio to use, and then to substitute it all in to finally come up with an answer. So that's all that. There's only one other type of problem I want to show you. So I'll just ask if there are any questions before I move to the next slide. Okay, the only sort of missing thing for this kind of problem is what happens if it's an angle. That's the thing that's missing, and it's basically the same approach. So in this case, I have two sides and I have an angle, but the steps are the same. What ratio? Substitute in and then solve, but in this case, this is where it gets a bit different. We solve using the inverse function. So I prefer to just start with the basic function and then work my way through. So you can see here that based upon where theta is, I've got opposite and I've got hypotenuse, right? So opposite and hypotenuse is SOHCAHTOA, sine. So that means the solution, I would always start like this. Sine of theta equals opposite 9 over the hypotenuse, which is 12. And you don't have to, but that equals 3/4. So therefore, theta equals sine inverse. Sine inverse of 3/4, which equals, and then you just plug it into your calculator. Make sure your calculator is in degrees mode though. I'm going to switch over to my GDC so you can see it in action. It's really straightforward. You just go trig sine inverse, and then just put in the operation that you worked out there, which is 3/4 in this case, 3 divided by 4. Close the bracket, enter. Make sure it's on degrees, of course, if you're doing it on your GDC. 48.59. I'll just write that down, then switch back over. So 48.59 degrees would be the answer there. On your scientific calculator, the sine cos and tan inverse functions are above the sine, cos, tan functions. So I'll switch back. And that's basically it. I've got my degrees in there. As far as I'm aware, I've checked this out, but we'll double check as well. You don't have to convert it into degrees, minutes, and seconds. So just having it to 2 decimal places like this is good enough. So the missing angle is 48.59 degrees. That's it. Anyone got any questions?
No.
Okay. I thought at least somebody might have said, will cuddles be okay? But you're all heartless.